So in this tutorial we are going to look at standing waves when they occur in air columns and pipes. And there's two special cases we're going to look at called open and closed pipes. We see a bunch of harmonics, or what standing waves look like, so what we want to do is understand why they have these particular shapes, and then ultimately to be able to determine wavelengths and corresponding frequencies for those particular harmonics. So let us explain how we develop, let's say, the first harmonic for a closed pipe, and then ultimately the first harmonic for an open pipe. Basically, these evolve because of boundary conditions at the ends. All right, so in a closed pipe, what it means is it's closed at one end right here, and it's open at another to the air from the outside. And in an open pipe, it's open at both ends. There could be a doubly closed, so I'm not going to show it here, but it would still follow the same general rules, and that's this. Nodes always occur at the closed end, and antinodes always occur at the open end. Okay, so let's take a look at this first, the simplest case. If I have to have a node here and antinodes there, the simplest standing wave I can produce is simply node to antinode, which is what I have here. So if I draw in from node to antinode as they have there, what we see, and this is the critical thing, is that this is a quarter of a wave. Pay close attention to why that's a quarter of a wave. Make sure you can recognize that in future pipe situations. Okay, so if I want to create the next harmonic, I always have to have a node here. I always have to have an antinode here. So to make a next complex harmonic, I simply add another node. So I have to add another node such that it's a quarter of a wave from the antinode and half a wavelength from the other node. So what I get is a wave that looks as seen here, node to node, or node, antinode, node, then antinode again. And then we have the dash one, which is a half a cycle later. So once again, we see that this is 3/4 of a wave. And then so on and so forth, 5/4, 7/4, 9/4. And what you want to notice, if you pay attention, is that these are odd harmonics. Okay, there are no 2nd, 4th, 6th, 8th harmonics with a closed pipe. They only come in odd numbers because, as we will see, the frequency at which this occurs is 1/3 the frequency of this, which is 1/5 the frequency of the first harmonic, etc. Okay, and that's just the way it works out. So an open pipe, same idea. We have to have antinodes at both ends because they're open at both ends. So a harmonic, to draw a standing wave, we need to put a node between those two antinodes, which would be right here. So I draw in the wave like this, and then the dashed line, and I look at how long that wave is compared to the tube. We see, and this is a little less obvious, but it's not too hard to see that that's only half a wave. And if we go to the second, more complex one, antinode, antinode, and then I want to now have two nodes between them. So I put them here and here, and so that I have antinode, antinode, and node between them, and I draw that in, which I'm not going to because it's already there. Then you can see why that's one wave. So it turns out that in an open pipe, you can have all the harmonics, and the rule that it follows is the same as fixed strings. In other words, the first harmonic is a half a wavelength, the second harmonic is a full wavelength, then 3 halves and 2 waves, which is the same as a fixed string. Okay, so you should be able to develop any one of those using the idea that the boundary conditions set how we start, and then you just keep adding nodes as you want to go to higher and higher harmonics. Okay, so let's do a problem where we're going to fill in some of these blanks. So it says, suppose each of the pipes above, and let's change the number from 0.334 to really just half of that, 0.188 meters long. If the speed of sound is 330 meters per second, calculate the wavelengths and frequencies of the first 3 harmonics for each of the open and closed. Okay, so I'm going to go back up here to the picture before we put our information, show our work. So essentially what I want to do is the same thing we did with strings. I ask myself, how many wavelengths do I have there? And we already said that's 1/4 of a wavelength. And that fits into a string, or excuse me, a tube of length L, which we were given, but we'll fill in the numbers later. So if I solve for L, or lambda, sorry I don't have much space here, I see that lambda is equal to 4 times the length. It's as simple as that. And for this one, if I say that there's 3/4 of a wavelength within L, then it stands to follow that L is equal to 4/3 the Excuse me, I wrote that down wrong. It stands that if we have 3/4 of a wavelength equals L, then lambda equals 4/3 L. Okay, so if I show my work down here, I'll do for the first harmonic, we said that there is 1/4 of a wavelength with an L, therefore lambda is 4L. 4 times 0.188 gives us a wavelength of 0.75 meters exactly. Okay, now if I want to find a frequency, I know that V equals lambda F. So F is going to be equal to V over lambda, 330 divided by 0.75 gives us 440 hertz. Okay, so I go up to here, I'm going to erase what I wrote before, and I have 0.75 meters. This is 440 hertz. Now I'm going to do the others by proportions. Essentially, if I've got 3/4 of a wave here, we already said this is 4/3, so this is 1/3 the wavelength, therefore 3 times the frequency. So 1/3 the wavelength would be 0.25 meters, and 3 times the frequency would be 1320 hertz. All right. And then if I want to go to the fifth harmonic, right, just to make sure we got it, we have 1 1/4 waves, so we have 5/4 of lambda in L. Therefore, L equals 4/5 of the original wavelength. Okay, so 4/5 of the wavelength. Make sure I'm doing that right. I think I might have done the lambda wrong there. Okay, so 0.8 times 0.75 is 0.6 meters. All right, so yeah, that was a mistake. I just, once again, made the goofy mistake. So therefore, we have lambda is 4/5 L. In other words, it's going to be 1/5 the original wavelength, which is 0.15 meters. And it will be 5 times this frequency, which would be 2200 hertz. All right, I'll leave it to you to try to do the other harmonics. Okay, so for this one, it's the same idea. We know that, really cut to the short, lambda is twice the length. Okay, so twice that length is 0.376 meters. And if we multiply, we do V equals lambda F. Okay, we see that there's a very big difference here. It's essentially 880 hertz for this one. So note that the first harmonic for the same length tube, compared for an open versus closed, is twice the frequency. Okay, so then this one will be 1/2 the wavelength because it's one wave that fits in there, right? Lambda equals L rather than 2L. So half of this is, well, whatever, 0.1718188 meters, and that would be twice 1760 hertz. Okay, I'll leave it to you to do the 3/2 wavelengths, but again, it all follows more or less the same pattern. Okay, so one last problem here. If a flute, an open pipe, is designed to play a middle C, which is that frequency, when all the holes are covered, if the speed of sound is 343, so this is at room temperature, I guess this one is at freezing point, what length will the flute be? So it's really just the reverse of what we had before. What are we given? We're given F and we're given V, so that tells us we can solve for lambda. So lambda is equal to V over F. Okay, so 343 divided by 262 gives us 1.309 meters. Now we want to relate that to the length of the string. Okay, so when all the holes are covered, this is assumed to be then the fundamental. All right, so what do we know about the fundamental for an open pipe? Well, if we go back up to the open pipe here, we see that lambda equals 2L. All right, so if lambda is equal to 2L, then L is equal to lambda over 2. So that's going to be 1.309 divided by 2. So the length of the flute is about 0.65 meters. There you go. And what would the length of a clarinet be for the same frequency? Okay, so lambda is still going to be 1.309 because we have the same velocity and the same frequency. However, for the fundamental, if we go back up, we saw that lambda is 4L. So the length of a clarinet is going to be lambda over 4 for that particular, and maybe not the whole clarinet, but at least the air column where that's being produced. So that would be essentially half of this, or about 0.32 meters. Okay, so pay close attention to those shapes of those standing waves and understand how we can get wavelengths from them.